All right, hello. Today we're going to be talking about similarity transformations and dilations. And so we've been speaking about that kind of since the beginning to say, hey, you can dial a shape bigger or smaller. And as long as the corresponding angles are congruent, well, then you'll be able to notice there is a scale factor that multiplies by every side to make it either bigger or smaller. So you could maybe double all the sides, or in the first section, or not the first section, in like a section two ago, the scale factor was by 10. Okay. And so I can scroll back and show you guys what we did, but um right about, oh, I guess it was back further than what I thought. All right, on this one here, notice because the corresponding angles match, okay, all of them, then the sides have a consistent scaling, okay? Notice the scale factor for this is times by 10, okay? So it's going to be 10. And how you can get that is you always put the image over the pre-image. Okay, and so the image side was 150 and the pre-image was 15, reducing that makes 10. And any of the sides, if you write as a relationship, like 40 over 4, will give you that relationship. So that's a scaling factor. And if it's bigger than 1, it'll make it bigger. If it's getting smaller, then the scale factor will be a number smaller than 1, like a half. Okay, so you can imagine all the shapes you have. If they're similar to each other, there will be a multiplication to get from one shape to the next. Okay, and so taking every corresponding side to get to the corresponding side of the image, you got to times it by something. And so it'll be something bigger or smaller than 1, depending if you're trying to get it to get bigger or smaller. We don't go negative really so much. There is a way to talk about negative, but we're going to say maybe not so much. Thank you. The end. Okay. I think I messed up my notes, which is fine. There they are. And so let's get back to our lesson for today. That's what we did yesterday, the good old side splitter theorem. Today, we're going to say, okay, what is going on here? Okay. We can have a similarity statement where we write the ratio in order as they're given, okay? And we could say, okay, we could write, say 15 goes with 12, and so we could go 15 to 12. If you put it in the order they give it to you, divide both by 3, it would be 5 to 4, okay? Um, to be frank, a similarity ratio, we don't necessarily do that very much, but it is true. Mostly we talk about scaling factors, like what are we going to times by to get from here to there? Okay. And normally we say, if they don't tell us what the pre-image is, we assume the pre-image is the one on the left and the image or the result is the one on the left, on the right. So we're trying to get from one to the next. And so how you get the scale factor, which we call K, scale, it doesn't have a K in it, but go figure. How do you get from one to the next? Well, you write the scale factor is given by the image over the pre-image, and then you reduce that fraction. Okay, so pick two sides that are cute. Okay, and so I could pick the 12 over the 15. So you could do image over the pre-image and reduce it. You get 3. Actually lies. Divide by 3, you get 4. Divide by 3, you get 4/5. So if you times any of the sides in the pre-image by 4/5, you're going to get the corresponding side of the image. And so an example of that working would be if I take, say, this one right here, 12.5, and 4/5 is 0.8. If I find the product of those, let me get out my calc. So I'm not about to do that without a calculator. Guess what I get? I get the related side, so 12.5 times the scale factor, which is 0.8 or 4/5. Okay, and I get 10. Okay, and you can check it on your calc too to say that. So since it's getting smaller, the scale factor is smaller than 1. Okay, if it's getting bigger, you could be doubling it. You could be timesing it by 3. You could be multiplying it by a fraction that's bigger than 1, like 5/4 or 8/7, or something like that. So if the fraction or number that you're timesing by a scale factor is bigger than 1, it'll make your answers bigger, your side lengths bigger. If it's multiplying by like a fraction smaller than 1, like 4/5, all your side lengths will get small. But remember, if they're similar, all the angles have to be the same measure, okay? Corresponding angles. So the angles don't change size. It's only the side lengths that get bigger or smaller. Okay. Now this is kind of weird, but you can deal with it. We're simply saying if you start with this blue triangle and you are going to make it bigger. I'll use green just so it looks cuter. Okay. The center of dilation is actually a location. Okay. And so you don't have to think about that. You can just literally just double each side and you can draw a dilated figure. Okay. But if you do it mathematically in a certain way, there is a way to have a center of dilation where it's kind of all focused. Every vertex is focused on that. And we're going to do a little bit with this. But the main gist is that we can double each side. Okay. And so if you are doubling each side or tripling each side or whatever you are doing, yes, you can do that. So are we doubling the side? No. Okay. Look at these ratio of sides. If you're starting with the blue one and going to the green one, and if we want to figure out what is that scaling factor, sometimes you can see it. Okay. It's apparent here that we're timesing each side by 4. Okay. Because notice we're going from 4 to 16. Obviously, 4 times 4 makes 16. And we're going from 3 up to 12. And that was a nice drawing. Okay, just kidding. 3 up to 12. Okay, not much better. And then we go to 2 up to 8. You can also write the ratio of the image length over the pre-image. So if you can't tell what it is, because maybe it's like a gross fraction, like 5/7 or 8/3 or something weird. Okay, and so you're going to do an image side. So we could do 8/2. If I look at these two sides here, any of the two corresponding sides, 12 divided by 3 was going to give you 4 as well. So the scaling factor is 4 on this one. And notice, since it's going to be bigger than 1, scale factor that doesn't have a K in it, but whatever. Scale factor is 1, bigger than 1, it's going to be an enlargement. Okay. Because if you dial the volume on your radio, you could going bigger or smaller. Okay, depending which way you're going. So your scale factor can be bigger or smaller one. Now here's where if you go negative, it's a rotation, okay, as well. Okay, so you're going to dial it bigger or smaller, and you're going to rotate it. So we're not going to play with that here, but that's kind of what happens. Now the next one, I had to kind of hijack a drawing because they didn't have any that were going smaller. So I found one that I could fix. Okay, so if you're going from this bigger trapezoid, and then you're going to move to the next trapezoid here. Okay, notice you're going smaller. Okay. And so if you write a ratio of the corresponding sides, okay, pick 2. I'm going to pick this one here, 2 and then 12. Okay, the image is the result. Okay, so the image over the pre-image. And so you're going to go 2/12. That's 1/6. And okay, this is reduction. Any of the corresponding sides. So if you did this one 1/6, that would give you the same ratio. And notice you are getting smaller. Okay. So any ratio of the corresponding sides should give you 1/6 when you reduce it. Okay. So here we go. Officially teaching about scaling factor. Okay. Here you go. It goes from the pre-image to the image. Okay. And what is the multiplication that you're doing to times each of the sides by to get from the pre-image to the image? How you find that is you put the image side over the corresponding side of the pre-image. If you can just see it, well, then do it. Maybe it's times by 2. Maybe the scale factor is a half. You know, like you don't have to necessarily do that, but sometimes when the numbers are tricky, it is helpful to do that. Okay. Both of these should be in the same units to make a unitless rate. That's why we did what we did in section 1. So scale factor K, that does not have a K in it, is what you multiply each of the sides by to get from the pre-image to the image. And so here we go. If these are going to be similar to each other, what is the scale factor? We're going to go 18/6, which is going to be 3. So every one of the sides is going to be times by 3 to get to that. So even though we don't know the bottom, say the bottom was, say, 2.5. If we times it by 3, we're going to get the bottom here, which is be 7.5. Okay, so I don't know what the bottom is. I just kind of made it up, but whatever it is, you're going to times it by 3 to get to the image piece. Okay, the next one. What is that scale factor going to be? If you go from here to here, again, we're going to assume that this is the pre-image and the one on the right is the image. Well, you're going to do 6/12, and that would be 1/2. Okay, so every side of the original is divided by 2 or times by 1/2 to get to the image piece. All right, next one. If you're going from here to here, you're getting smaller. Okay, so this is going to be a reduction. Okay, they're all dilations because you're dialing them bigger or smaller, but this is an enlargement. Okay, and then here you're going to be reducing it. And the scale factor is going to be, again, write the ratio of any corresponding sides. You should get the same answer. I don't really want to do 7.5/5. Okay, how I would deal with that would be I times the top and bottom by 10. Okay, to get rid of the decimals, so it'd be 75/50, and then I would divide everybody by 5, and I would get 15/10. I would divide by 5 again, and I would get 3/2. I should have seen that earlier. So 3/2 is going to be the answer, but you might not choose to do the fractiony ones. Okay, you might be like, how about we stick with the bottom, the 6 and the 4. So let's do 6/4. Again, reduces by dividing by 2. And that's going to be 3/2. And because 3/2 it is a fraction, but it's bigger than 1. That is weird. Notice this is not drawn to scale, is it? That's really silly. Look at this 4. Look at this 6. Okay. This looks like it's bigger than the side right here. So it's obviously going to be not a reduction, even though it looks like it is. This, I guess, was an enlargement because this second diagram is not drawn to scale. Well, that is kind of ridiculous. I'm sorry. If this was drawn to scale, it would look like bigger than the original one, wouldn't it? Okay, so just be alert. I guess that happens where you're like, oh, I didn't draw it to scale very well. I got this from the textbook. So this is actually an enlargement if you actually look at the numbers. So anyway, that is not going to typically be a problem, but this one here, the scale factor, if you go from A to B, and you will see this again. Okay, so going from A to B, notice you're getting bigger, aren't you? Okay, because B is bigger than B is your end result. Okay, and so the length you have to find a corresponding length. Now, don't count slanty. That's just weird. The bottom of this is 4. The bottom of this is 8. So you do the image, okay, which is going to be from A to B. So you're going to do B over A. So you're going to do 8/4, which is going to be 2. Okay, notice each side is going to be doubled the original side. Okay, and then if you go from A to B here, okay, count sides that make sense. So like, I don't know that I want to count the bottom because it's all decimally, but this vertical B is 2, and this vertical length is 4. And so we're going to do B over A. And so B would be 2/4, which is half. And notice if it's going from A to B, it is getting smaller. Okay, and this every side is half the length of the prior one. Okay, so you got to figure out it's going from A to B. Well, then put B over A. And if you need to write B over A, you can. Okay, keeping track of like which way is it going. Okay, put the image over the pre-image. Okay, moving forward. You start with a picture and you're going to either enlarge or reduce it. Okay, so you're going to go to like a copy machine and be like, okay, let's make it bigger or smaller. Or you're going to go on your computer and like enlarge or reduce a size. Okay, so the larger picture has a width of 2.5. Oopsie, that's just classy. So this is 2.5 or 2.5. Okay, and the smaller one has a width of 1.5 or 1.5. Okay. If the smaller picture is the result of a reduction, so you're going from big to small, okay? So you're reducing. What is the scale factor? So you have to put the image over the pre-image. So the result was the smaller image. So you're going to do 1.5 over 2.5. And you can't, you can't leave decimals and fractions. So how you deal with that would be times by something. Just like when you're reducing a fraction, you divide both sides by something, top and bottom by something. You can also times top and bottom by the same number. So if you times the top and bottom by 10, you're going to get 15 over 25, which we can reduce now. And so we can divide them by 5 and you get 3/5. So the scale factor is 3/5 of what it used to be. Okay, so it is a reduction. Your scale factor K is 3/5. Now the deal is this. We're gonna try two more things. Okay. One of them is going to be about that center of dilation. Okay. And so, and it's kind of cute. Like it actually makes it more numerical. Remember, we did all the reflections and rotations where I'm like, here's a triangle. Let's rotate it about the origin 270 degrees. Okay. And so you did, and how you did it was you took all the points of the original pre-image and you did like you did negative y and then x or negative x and then y. You did all the different rotations. So rotation of 270 would be a y comma negative x, I believe. And I don't always memorize those, but you can look it up and so can I. So the thing is that we're going to kind of do that with shapes. Okay. And so here's not a cute shape, it's just a segment. So if you start with this segment right here, okay, if that's your pre-image, and our segment has 2 points, one on each end. And so if this point happens to be like 1,6, I think that's roughly what it is, and this point is say 2,3. Well, if you want to do a dilation of like a triangle or do a dilation of a segment or like make it bigger or smaller, the crazy thing is that you can take the vertices of it and do math to all the vertices, and it will actually dilate your figure. Okay, so example. Okay, watch this cool move. If I start with the points 2, 6, and 1, 2, 3. Okay, so here's your points of, you remember we had a table. We're like, okay, 1, 6. Okay, these are my pre-image points. That's point M, and this is point P, and you got 2, 3. If I want to double the length of this segment, okay, all I do, okay, is I take 2 times both X and Y. And so doubling each of these points, like, okay, so double X and Y, okay, I'm going to do 2 and then 12. And then if I double the other point, you get 4 and say 6. Well, if this point right here is 2, 12, and down here, P is P prime, okay? It would be M prime, and this would be P prime, is going to be 4, 6. Look at this. It should be double the original segment. And technically, it's actually twice as far from the origin. Okay, so it doubles it. So if you tripled each point, it would be triple the distance from the original function too. So it's kind of weird that it does two things. It actually magnifies, enlarges or reduces, and it also brings it closer or further from the origin from the original shape as well by that same factor. So it's actually kind of cool. Okay, and so we can practice that here to be like, okay, let's graph a rectangle think that's what it is. So we go to -2, -2, and that's E. And then -2, 4, that's F. And then 2, 4, that's G. And then 2, -2, that's H. So we've got our pre-image, okay? These are our pre-image points. And then you can, like, I'll tell you, but like one could say, okay, I'm going it to be twice as big and every point to be twice as far away from the origin. Well, then you would double the X and Y coordinates of each point. If you wanted to do triple, okay, the distance from the origin, okay, the center of rotation of dilation is the origin of how we're going to figure it. Are there other ways? Yes, we're not going to go there. Okay, so if your center of dilation is at the origin, we are going to dial the shape bigger or smaller so that every segment length, okay, of the figure is going to be that factor bigger or smaller, but also that factor closer or further from the origin. Okay, so if we times each of these by a half, okay, 0.5, you can use your calc if you need to, you get -1, -1, -1, 2. So I'm just taking half of each ordered pair values. So you get 1 and 2, and then 1 and -1/2. And so when I graph the image, okay, we already got the pre-image on here. If we graph the image is -1, -1, and that's going to be E prime. Notice it is half the distance from the origin, isn't it? Okay, half the, because you're taking half. Okay, very cute. -1, 2. Okay, this is F prime. Again, it's half the distance from the origin of the original point. And this segment F to E prime, F prime, E prime, is half the length of the original segment. If you count the little cubes, you can do like 1, 2, if I can count, 4, 5, 6, and this should be 3. Okay, so yeah, it's half the length of the original segment. Okay, and so because our scaling factor K is half. And then we've got G prime, and then over here would be H prime. And there we go. Okay, so each point is half the distance as the original is from the origin. If you times it by 2, it'd be twice the distance from the origin. Okay, and so we're going to play with that here. These are a little bit more less lovely. So this is the center of dilation here. And so you just, one thing that I would say is this. Let me zoom in. I hate that blue line. Okay, so if that's the center of dilation right here, I don't really scratch it out. I meant to highlight it. Okay, you've got to look to be like, which one's the pre-image and which is the image? So this is K, that's the pre-image. This is the image. So watch for that, okay? Then we're going to play on that origin thing. We're like, oh, every point, if you're here and you get to here, it's twice as far. Okay, your scale factor must have been 2. It goes twice as far away. If you are here and you bring it in, your distance from the origin has been halved, so your scale factor is a half. So if this is your center, just like the origin is your center here, we find the distance to a common point on both figures. Okay, and you have to say, well, the distance from here to here is X. Okay, awesome. That's really helpful. Just kidding. And then the distance from here to here is 10. No, that's a lie. That's 15. Okay. It appears that this actual distance is 10 here. Well, if we can subtract, we know this is going to be 5. And so if you're doing, so if the overall distance is going to be 15, and this part is 10, and this part is 5, cool, great. They are like, well, what's the scale factor going to be? Well, first of all, it's going from K to K prime, okay? All right, that was real helpful. It's going from K to K prime. So notice your K values are smaller, it's getting bigger. So that would be an enlargement. Okay. So your scale factor has to be bigger than 1. Okay. So that's just kind of look at the picture, read what's going on. And so the distance, so to find the scaling factor, we have to do the image over the pre-image. Okay. And so if we knew any lengths of the sides, we could write the image side. Like if we knew this length and put it over this length, we could find the scale factor. But an alternate way to do it is to work with that distance from the center of rotation. So the distance to the image, it looks like from here all the way to K prime is 15. And then the distance from here to the pre-image is actually only 5. So how much bigger are you making it? You are making it 3 times as big. So your scale factor is equal to 3. So that was kind of a lot, okay? And does it look like it's 3 times as big as it originally was? Well, yeah, it kind of does, okay? Ish. I mean, not perfectly. So you can write a ratio of the corresponding sides, image over the pre-image, but if you don't have that, you can write the distance from the center of rotation to the image over the distance to the pre-image, and that will give you the scale factor as well, okay? Because any dilation from focused on a certain point, okay, where you connect all those points to that center is going to actually have that same ratio as the dilation that happens or the reduction. Okay, so this one, again, the center of rotation or center, I keep saying that, the center of dilation is right there. And then which one's the pre-image and which is the image? Okay, so it goes from K. K looks like this smaller one right here to the larger one, which is K prime. So this is as well as an enlargement, okay? And then you're like, well, it looks like it might be doubling or something. I don't know. We'll look and see. But how you figure that out is you do the image over the pre-image. And if you don't have the length of the corresponding, you wanted this over this, like sides, but like we don't have that. Okay, so let's find the distance from the center of dilation to the image. So this overall length here is going to be 3. Okay, so that's 3 over the distance to the pre-image, which is 2. So that is going to be our scale factor, 3/2. So it's going to times it by 1.5. Okay, so it is bigger than 1. The value of X is actually 3. So the distance from the center of dilation to the image over the distance to the pre-image will give you that scaling factor as well. It's a little weird. Now, this last one, we're going to actually get out a ruler, okay, and say, okay, if this is my pre-image right here, okay, and this is my center of dilation, okay, can we dilate this, okay, to make it bigger or smaller? We're going to dilate it and we're going to make it an enlargement, okay? And I can't do this the best on my computer, so I'm going to have to describe what I'm doing, okay? We're going to use centimeters, okay? And so we're going to measure the distance from O to B in centimeters, okay? And we are going to get 2.6 centimeters. And if we want to double this, we need to make, in line with this, keep on trucking, double the distance from O. So we're going to make this distance to be times 2 is going to be 5.2 centimeters. And so we're going to draw B prime. Okay. And so if you double the distance, you're going to double the size of your figure. Okay. And so if you measure the distance from the center of rotation or of, I keep saying that, the center of dilation from O to C, I got that to be 3.2 centimeters. Now, it's possible with the photocopier that yours is a little bit different, but use your centimeters. Okay, and we're going to times it by 2. And so our distance to C prime should be twice that distance. Okay, and so if you double that, you're going to get 6.4 centimeters. And so again, if double that, okay, and so this will be C prime. So these two distances should be the same. And then the last one we're going to do is going to measure the distance from O to A. And I believe last year when I did this, I got it to be 2.2 centimeters. And if I times it by 2, I'm going to get 4.4 centimeters. This is A prime. And if I connect these prime points, I should get a figure that is twice the measurement of each side, okay, because I did a scale factor, and at each point will be double the distance from the center of a dilation. Okay, so it's kind of a cool way to dilate bigger or smaller your factor. If you're going to times it by a half, it would make your figure smaller and half as far away. So that's what you're going to practice on your homework. All right. Thank you so much. I hope you have a great day.